I want to walk you through this assignment on volume calculations. This is meant to be done after the groundwater because you need some groundwater stuff for this. It's really before the runoff calculations, although we do runoff calculations here, we don't tell where that number comes from. You'll see in the next section there. So both these problems in here were exam problems in a previous life. The first one here, we're designing an outdoor track and field facility. Impervious area will be about 3 acres. Now there is something called the simplified method, which in Pennsylvania most municipalities have it set according to state guidelines that if it's under 1 acre, you can use the simplified method, which you just have to capture the first 2 inches of runoff. So that's what we're going to do here, even though it's bigger than 1 acre. So to come up with the volume, you have your area that the water's landing on, and then you have 1 inch of water on there, and then you just multiply 1 inch times the area, and you get a volume of water that you have to handle. You have to do unit conversions, obviously. So now we're going to put that water, we're going to run it off from our 3 acres, and it's going to go into a trench. So the trench is 300 feet long, and it's 12 feet wide, and now it's going to have, well, we got to determine how deep it has to be. Has a porosity of 0.35. So you remember that from the groundwater. These are my little gravel stones here. The space available for the water then is 35% of the total volume. So you have 2 inches of, I wrote that wrong, 2 inches of runoff on the 3 acres. Multiply that together, you get a volume. Then you got to put that volume into this trench, and so you have to figure out how deep it needs to be. So the total volume of this, which is the 300 feet by 12 feet times the depth times 0.35 is the volume available for water. So you need to solve for the depth of that. That's a question mark, by the way. And then, and this is also part of the simplified method, half of that, or at least 1 inch of the water, must be infiltrated. So it's got to go into the ground on the bottom here. So we have to infiltrate it. It says infiltrate, believe me. The hydraulic conductivity of the soil equals 1.5 feet per hour. How much time is required to infiltrate 1 inch of runoff from the impervious surface? So 2 inches, multiply that area was the total volume. We got to take half of that, or 1 inch times that area, and we have to infiltrate it. So how much time is that going to take? Well, we can take that from Darcy's law. Q equals K times the gradient, change in head, with length, or with in the direction of flow. Sometimes we call it an I. And if we do the big Q here, we need area here, and that's the total area. So we have the total area. The flow is going this direction down into the ground here. So the cross-sectional area would be this area up here. Oops, didn't mean to zoom, but that'll do the job. So we have the area, we have the hydraulic conductivity. What is the gradient? Well, if we make the drain underneath here really fast, so it gets rid of the water really fast, then as soon as the water hits the bottom here, it gets drained away. So when the depth drops 1 foot, then the head drops 1 foot. Head that well, but we can kind of make the assumption that as the head drops 1 foot, or the water drops 1 foot, the head drops 1 foot, and so then the gradient, the change in head with depth, or again we sometimes call that I, equals 1 foot per foot. So we can make that assumption if we say once it hits that bottom, it's just taken away. So there's basically 0 head at that. And we're going to make that assumption on the next problem too. So from that, again, calculate, solve for the depth here, and then solve for the time it takes to get the water out of there, get 1 inch infiltrated out of there. This next problem references a reservoir system in Sri Lanka. I visited Sri Lanka 30 years ago and was fascinated by the reservoir system, and then actually put together a little proposal about, I guess it was 12 years ago, to study flow in the reservoir system. It's really cool. Didn't get funding for it. That's about the time I came to Messiah. But I'm tempted to give you the whole story here, but I'm not going to. If I do, I'll insert it back in this video. But what we have here is we have a tank, they call it there, or what they call it, and it's 40 meters wide, so into the paper it's 40 meters, 60 meters long, so that's the dimension right here. The tank is built on an impermeable clay layer. It's impermeable down there. And then the dam is 5 meters in this dimension, so the water is going to flow through the bottom of the dam there, 5 meters in that direction, and 40 meters again into the paper, and it's concrete. There is a 0.8 meter layer there that the water actually flows through, so the water doesn't throw through the concrete, it flows through this area here. The sides of the tank, again, the end that's facing us and the other end can be assumed to be impermeable, so the only way the water gets out of here is through the earthen layer, except that there's pan evaporation. What's pan evaporation? We didn't talk about that. So pan evaporation, the idea being that you measure it by, you have a pan, it has water in it, and you leave it sit out, and if it drops 0.9 centimeters per day, that's the pan evaporation. So to come up with the evaporation rate out of the top of here, so it's coming in at 31 cubic meters per day, and then the water balance is some of it's going out through evaporation, some of it's going through this earthen layer here. So you solve for this, the evaporation, then you have the in, you have the out, the rest of the out has to be going through the dam here. And then you have then the flow through the dam. You have the area of the dam, 0.8 meters times 40 meters into the paper. So we have the change in head with length. So the change in head, well, you got 2.1 meters on this side, 1.1 meters on that side, so you have the change there. Length is the length along the direction of flow, the 5 meters. So you have that, and then you solve for the K. Now I put the minus in front of there because, again, the change in head per length is actually negative in the direction of flow. So you have the flow by volume balance. You have by measurement, by observation, you have the change in head length. You have the area. You solve for the hydraulic conductivity, and then check this chart down here to see this table, to see what description fits the hydraulic conductivity you found. And notice here there's a couple orders of magnitude for all of these. So, and they overlap. So based on that, come up with what type of soil it is. All right.